Hi everyone, welcome to our YouTube channel. In this video, we'll be learning about polynomial regression. So just to give you a context, earlier we have learned about linear regression, and one of the many assumptions that we have learned is the input and the output should have a linear regression relationship, right? So what we mean by that is, let's say this is our 2D axis, and we have certain points. So our x-axis, sorry, this should be our y-axis. And our x-axis should have a linear relation. The point should have a linear relationship between the x and the y-axis, right? So my question to you is, what if we have a non-relation? What we what if we have a non-linear relationship? For example, a quadratic relationship, or let's say a cubic relationship. I hope you understand this is y equals to x squared, and this one is y equals to x cubed, right? So in that case, can we say that we can use a linear regression anymore? The answer is yes, but with a bit of tweaking, right? We cannot directly apply linear regression. We have to do a little bit of tweaking. And this is what we call as a polynomial regression. So whenever the relationship between the features and the target variables, right, is non-linear in nature, it follows a particular nature, a particular function, let's say a quadratic function, cubic function, sinusoidal function, or any other function, we can tweak the features to form a polynomial feature. All right. And that itself falls a, or forms a polynomial regression. So in simple words, linear regression with a bit of tweaking helps us form a polynomial regression. What are the tweakings that we would want to apply? We'll come to it. Okay, step by step. So let's see how we apply the same using coding. And meanwhile, as I write the codes, I'll try to explain how do we do this particular tweaking to make our variables from linear to polynomial in nature. All right. So let's see how it works. Okay. So the very first step that we do over here is collect the data like usual, right? We know the few steps that we actually undergo. First is data acquisition, followed by data pre-processing. Then we do the EDA, followed by feature engineering. And finally, we do the modeling. That is the machine learning modeling. And after that, we do the evaluation. We have also learned about the different evaluation metrics for any regression model. All right. So as I said, the very first part, we do the data acquisition. So for that, first we need to import the different libraries, right? So let me, along the way, create the notes. First thing that we do is data acquisition. I'll import the necessary libraries. So import necessary libraries. Now I want to import NumPy. I want to import pandas and a visualization tool. So let's import Matplotlib. Okay. Again, we'll also import the warnings library just to get rid of the unnecessary warnings. So import warnings and warnings dot filter warnings. Ignore, right? Done. Now we want to input the data. So df equals to pd.read underscore CSV followed by the name of the CSV file. So we already have the CSV file over here and I will be using the temperature data set. So let me just copy the name from here. Okay. Now if I simply say df.head, now df contains this particular CSV file in the pandas format, right? Since we have done pd.read underscore CSV. So if I simply say pd.read, sorry, head will get the values, right? This is how the data looks like. The first 5 lines of the data looks like. So it has two columns, day and temperature. Great. Now, before even visualizing or anything, let's quickly do the pre-processing so as to, make the quality of the data correct. So as I said, this is the first step. Next step is data pre-processing. And by the way, in a particular data science scenario, this is something you should always remember, the steps, right? These are the steps that we always have to follow. Like for software development, we have SDLC, software development lifecycle. For machine learning, we also have something called as a MLDLC, machine learning development lifecycle. All right. So data pre-processing. The first thing that we'll do is check for the null values. So check for null. I'll simply say df dot is null dot sum. That's all. Okay. So no missing values. Great. Let's also check for the duplicate values, if any. Df dot duplicated. Let me just simply put it. Okay, so no duplicate values as well. Great. Now you can check for any other things as well, but I know for a fact that this data is correct. So let's not waste further time. Let's also just see the information, right? So this is also a very important technique. Information about data, right? So we do df.info. It says day and temperature non-null. Basically, we already found there is no null values and both are integer and float. So everything seems perfect, right? And nothing that I would want to do over here. Let's quickly find again, for EDA, there is nothing as such, but I'll still, just for the practice purpose, right? We'll also mention this. So very first thing that I want to do is statistical summary. Again, to be very honest, all the steps that I'm doing over here is kind of irrelevant. But what I'm doing is just to make you acquainted with the data science process, the MLDLC methodology, right? So first data acquisition, then data pre-processing. Again, there are various other steps in data pre-processing as well. Just to give you a context, these are some of the things that we usually do. Again, we have done EDA. So I just find the statistical summary for the sake of it, right? But ideally, we also have to do univariate analysis, bivariate analysis, multivariate analysis, so on and so forth. And this EDA and data pre-processing is a very iterative term. We do EDA, we understand certain things, we again do data pre-processing. Again, once we have done those data pre-processing, we move to EDA. We find any other things that need to be pre-processed, we again move back to the data pre-processing scenario. We keep on doing this to and fro again and again in a loop till the data quality becomes really good. And then we move to something called feature engineering. As of now, the data is not that difficult. So yeah, I mean, that's totally fine. So df.describe. This gives me the count, mean, standard deviation, minimum value, maximum value, and the percentile values. 25th, that is the first quartile, the median, and the third quartile values. All right. Now, what I really want to do is I want to understand the data. So I want to plot the data and see how it looks like. So what I'll simply do is pld.scatter. I want a scatter plot followed by df of day, right? So we have day and temperature. So take this one over here and df of temperature. Let me just put a semicolon over here just to get rid of this particular line. Or you can also write pld.show alternatively. Okay, so the data that we get is somewhat a cubic function. So data here is of the form um, just change the color. Data is of the form y equals to x cube, right? This is how a y equals to x cube looks like. So a simple linear regression would not really fit well, right? Let's just try with a simple linear regression how it works and see how the evaluation metrics perform, right? But before going to the modeling, the next step ideally is let me also put numbers so that it's easy for you to remember. First step, data acquisition. Second step, data preprocessing. Third step, EDA. And again, while it might look redundant, it is very, very important that you always remember that you have to perform all these steps, right? It should be in your muscle memory. Next, we have something called as feature engineering. Also, just to be clear, I'm not performing all the processes under each hood. So data preprocessing has many other things. EDA has many other things. Feature engineering will definitely have many other things. All right. Here we do the feature scaling. We do, encoding from string to numerical values. There are so many other things, feature selection, feature extraction, so on and so forth. Okay. What I'll do over here is just the trend test split because that also comes under feature engineering. Okay. So I'll simply say x equals to df of data, df of day, right? The first part. And y equals to df dot temperature. So x and y has been fixed. This is the splitting of the data into x and y or the target and features. So let me also write it over here. Next, we'll do the train test split. Or so from sklearn dot model selection, import train test split. All right. So here what we'll do is, I hope you already remember, xtrain, comma xtest, then ytrain, and ytest, right? Equals to train test split of x comma y followed by the test size. And I want to keep the test size to, let's say, 70%. I mean, 30% should go to the testing side and 70% should be used for training. And I also have to give a random state. So random state equals to, let's say 2 or 42. Okay, great. Test size. Invalid syntax. Okay. All right. So I missed this comma over here, right? Good. Thing should work. Yes. So this is what I'll say for feature engineering. I mean, I'm not doing any feature engineering, but then, yeah, just for the sake of it. Then let's just do the modeling. So I'll say modeling and evaluation. You can take it in two different steps as well. Modeling for step 5 and evaluation for step 6, or modeling and evaluation, whatever you want. Okay, because why am I taking it in the same step? Because modeling and evaluation comes simultaneously. We model we use a particular model, we evaluate that model. If it doesn't work properly, we tune certain hyperparameters or we move to the next model, right? So we keep on evaluating each and every model once we create those models. So it comes in sync, it comes in simultaneously. All right. So the first model that I want to take is linear regression and see how it performs. So let's quickly say linear regression. So from sklearn dot linear model import linear regression. Okay. And I'll just take an object to the class linear regression so that I can use it. Okay. Now let's train the model. So model dot fit inside X train and Y train, right? So X train comma Y train. This is my training part, and then we want to predict, right? So let's call it as prediction or predictions because we have multiple predictions. So model dot predict what? X test. Based on your training from the from the X train and Y train, predict the Y values for X test. Okay. So this is our modeling. Now we need to evaluate the model. Okay. So let's just call it as evaluation, and this was my modeling. Okay. So what are the things that we'll be using? We can use MAE, MSE, RMSE, so on and so forth. But here what I want to use is simply the R2 score. Okay. We'll just evaluate the model based on our R2 score. Ideally, you should use all, or depends on the business scenario, what you want to use as a evaluation metric. But R2 score seems good for our use case. All right. We need to increase the R2 score. That's all. Okay. So from sklearn dot metrics import only R2 score, right? Now what I'll do is I simply say R2 score of I test and predictions. So I want to find the R2 score between the y-test, the actual values, and the predictions. That is what the model is predicting. So let's see what is the R2 score. The R2 score is 0.51, that is around 51%. Or you might want to say 52%, 51.59, which is not a very good R2 score, right? And why is this the case? Let's see a visualization how our linear model or how the best fit line is getting created. Okay, so let's see the visualization of the same. So what I'll do is plt.scatter, and then we'll say plt.plot between x test and predictions. Okay, and let's just quickly give a color because otherwise it might not look that good. Let's take it as red. Let's also put a semicolon. All right. So this is what our line looks like, the best fit line. And we cannot blame it for anything, right? Because we know that a linear regression line would only be a straight line. And it is trying its best to fit most of the lines, the most of the points. However, it cannot fit through all the points because the curve itself is not linear in nature. So it is trying its best to fit most of the points. However, since the data distribution is in a very different way, we are getting an R2 score of 52% around approx, right? So what we want to do in this case is we want to use something called as a polynomial regression. We want to tweak our points in such a way that it fits the given points. Okay, that's what we are going to do right now. So instead of linear regression, let's use something called as a polynomial regression. Okay. Now, the very first step for polynomial regression, as I said, it's not a magic. We are simply tweaking the same of linear regression into polynomial structure. So first thing we want to do is transform into polynomial or make the polynomial transformation. All right. So make polynomial transformation. All right. So what I'm going to do is from sklearn dot preprocessing, import polynomial features. Okay. Now, let's just call a variable poly equals to polynomial features, and I have to give a degree. So here I can see the degree should be 3. You can take higher degrees as well. We'll see by changing the degree, okay, manually. So as of now, I know the degree is going to be 3 because I can see from the graph itself. Not always is it so clear or so evident like this. Okay. Now what I'll do is, so xtrain, let's call it as xtrain poly equals to poly.fit. Or let's together do the transformation as well. So poly.fit transform, right, xtrain. So what I'm doing over here is I'm transforming xtrain using the degree 3. What is happening? And I'll show you. Just give me a moment. Let me also write it for the test. So xtest, or let's call it as xtest poly as well. Because I want to show you, I want to keep xtrain and xtest as it is so that I can show you how the polynomial graph changes with the linear graph. Okay. So xtest poly equals to poly dot. Here we'll only say transform. Transform what? Xtest. Okay. So what did we do over here? Let me make you understand this. Uh, okay. So what did we do over here? Initially, we had two columns, right? Day and temperature. Temperature was our target, so we cannot do anything about it. But what we can do is we can pick the features. Am I correct? So initially, let's say we had day something like 1, 2, 3, so on and so forth. Okay. By using this term, right? Polynomial features degree equals to 3. What did we do is we transformed these features into something like this. So now we have we have day square, we have day cube. Okay. So 1, 2, 3, 1, 4, 9, 1, 8, 27. Now this is what we have, right? So simply by saying polynomial features degree equals to 3 and then training the x-train data and the x-test data using poly is nothing but a object to the class polynomial features. That is, it is transforming all the values of day to day square, day square, and day cube. All right. Now, by doing that, what it is finding is it is giving different weights to day square, and day cube. Okay. So think like this. It is giving a weight of omega 1, omega 2, and omega 3. Okay. And it now predicts y equals to omega 1 into day plus omega 2 into day square plus omega 3 into day cube. Okay. Now what happens is it doesn't choose between any of this x square, that is day square or day cube values. No, it only, it does a very, subtle kind of an experimentation. It gives weights, different weights to the different variables. And by assigning these weights, it gives more preference to a particular variable. So for example, I hope you understand this particular part, right? Let me just clear this. If you understand this, so for example, let's think of a line as uh, y equals to, let's say 3x squared. All right. Now, let's say for omega 1, you understand what is omega 1, right? The coefficient for x. The machine learning itself has given 0. For omega 2, that is the squared one. Okay. Or let me also write it over here. Y equals to omega 1 x plus omega 2 x square plus omega 3 x cube. Okay. So for omega 2, it has given something like, let's say 3. And for omega 2, it has given something like 0.01. So automatically, by assigning the different weights, it is giving more priority to omega 2. That is, in simple words, y becomes a function of x square. That is, it becomes a quadratic function. I hope you understand. Similarly, if the function was something like y equals to, let's say, 4x, then automatically omega 1 would have got the more priority. So let's say this becomes something like 2. This becomes 0. This becomes 0. So automatically, our equation would become a linear equation. Again, what if the equation was y equals to, let's say, something like, let's say, x cube plus 4x plus 3. In this scenario, we'll get different values of omegas. So omega 1 would also have some value, let's say 2. Omega 2 will also have some value, let's say 2.5, and omega 3 will also have some values. Let's just call it as 3x square. So let's say 2 again. Now, it cannot really say that a particular equation is cubic, quadratic, or linear based on the equation, because we know that an equation cannot always be a pure cubic equation or a pure linear equation. It can have multiple coefficients, right? I'm sorry, not coefficients, the cubes, the exponents, right? So based on these exponents, the machine learning itself assigns the weights. And based on these weights, the model gives preference to the different exponential variables. All right. I hope I was able to make this particular thing clear. So what I'm essentially doing over here is from day, which was in linear fashion, I simply converted it to, when I say degree equals to 3, it will automatically create day, day square, and day cube. If I said degree equals to 4, it will also create another variable, day to the power 4, right? If I say degree 2, then it will only say day and day square. And based on this, it will automatically create the values. And now it will try to assign the weights based on how those models are fitting. All right. So this is what polynomial regression does. Just this snippet of code we would want to apply before applying linear regression, so as to tweak the linear model into a non-linear model, right? All right. So once we have actually tweaked it, let's quickly go ahead and apply the linear regression. Now, again, the same thing that we have done earlier. Okay. So what I'll do over here is I'll simply apply but there needs to be certain small changes. Instead of xtrain, we have to do a xtrain poly. Also for ytrain, we have to do a ytrain poly. Okay. And here also we have to do a xtest poly. Great. So our modeling is ytrain poly is okay. Ytrain poly is not to be used because we are not transforming the y, right? We are only transforming the x. So we are good with this. Great. Now let's quickly evaluate our model. Uh, think everything seems well. Y test versus predictions. Yeah. So see how our model actually increases the R2 score. From around 52%, we are now getting around 91%, 91.4. From 51.59%, we are getting a 91.4%. So good improvement in the R2 score, a good improvement in the variability of the model, right? Now, if I want to show you how the visualization now looks, let's see that as well. Just give me a moment. Do I need to change anything? We would want to find our predictions. The predictions is this one. I could also have written predictions underscore poly or something like that, but that's okay. I would not want to change x test poly because I want to plot the graph on x test, so that seems fine. Okay, we get a weird graph. This is essentially because, let me explain why are we getting something like this. So we did the trend test split, right? So what happens is, let me also explain this, should be very, very clear to you. So let's say initially we had the data something like this, x equals to, let's say, we had something like 1, 2, 3, 4, 5, so on and so forth. for y, we had values like, let's say a quadratic equation. Okay, so we had values like 1, uh, 4, 9, 16, 25, so on and so forth, right? So basically, y equals to x squared. Now, when we did the trend test split, what happened? We took 30% of the data for testing phase. The rest 70% we took for the training phase. Now, this 70% of the data we took from here and there, right? It was not a very linear way of taking. So suppose we had the data something like this. We took the training data randomly from some part. We took this part of the data, we took this part of the data. So it's not a very linear way of taking the data. And as such, what happened was the data got shuffled. So now our X test probably becomes something like this. Let's say 4, 1, 5, 2, 3. So predictions will also become something like 16, 1, 25, 4, and 9. Do you get me? So what now happens is the points are 4 to 6, 416. This was the first point. From 416, the graph jumps to 1, 1. From here, it jumps to 5, 25. From here, it jumps to 2, 4. Then to 3, 9. So what happens? This point doesn't go linearly like this. From this point, it probably jumps somewhere over here. Again, from this point, it jumps probably somewhere over here. From this point, it jumps somewhere over here. So you get this zigzag kind of a pattern. All right. Now, how to get rid of this? There is two ways. One is we can simply sort out our X test values, or we do not do the trend test split at all. So usually in industries, we typically do not visualize data because the data in itself is very large, right? So visualization is not needed. So this sorting and everything is not needed. So what I'll do is, let me just create this model again, just for the sake of visualization without doing the trend test split, okay, from scratch. So let me just save visualization. So x equals to df of d and y equals to df of temperature. Now, let me create the linear model first. Okay. So LR equals to linear regression. Now, LR dot fit x comma y. Now what I'll say is y pred. So I'll just take y pred as y linear equals to LR dot predict x. Okay. So this becomes our linear model. So y lean becomes our linear lean. Now let's also take a polynomial model. Okay. So here what I'll say is poly equals to polynomial regression. And the degree I want to take is 3. Okay. Now x poly equals to poly dot fit. Let's do the transform along with it. So fit underscore transform x, and let's do the same for okay, it's okay because we only want to take change there's only one x, not trend and test, right? Cool. So now I want to take the linear model. Also, let's create another model, same model, but just to be on the safe side. I mean, it's not to be on the safe side, just to follow the correct order, right? So what I'll do is PLR, that is polynomial regression, but it's simply a linear regression only. I could have taken LR, by the way. It's not a problem. Okay, so PLR equals to linear regression. Now what I'll do is the same thing. So like I did LR.fit, I'll do PLR.fit. So I'll simply say, instead of LR, I'll say PLR. We could have said LR.fit and not taken this line itself. Again, why we are taking? Just to follow the sequence. Okay, not needed. So I'll simply say X poly, comma Y, and Y poly now. Y lean I have used earlier. Now Y poly equals to PLR.predict, right? Predict what? X poly. Okay. So now we have two lines. One is X lean, one is Y lean. X poly. I'm really sorry. One is Y lean, one is Y poly. So now let's see the visualization. So what I'll do is, first thing, PLD dot scatter X1. See? Okay. Name polynomial regression is not defined. I'm sorry. It's polynomial features. Right. So this is the graph that we are getting. Okay. Now let's also put the Y lean and Y poly. So PLT dot plot Y lean. Let's take a color. Let's take something like red. And let's also give a label. Okay. And let's say PLT dot plot X comma Y poly. What other color can we give? Let's say yellow. And we give a label as polynomial. Okay. Finally, we say PLT dot legend so that the legend also shows up. And let's also say PLT dot show. So this is exactly what you see. These are the actual points, the points of temperature. This is my linear line, which we have already seen, right? And this colored line that you see, the yellow colored, is actually my polynomial line. So by creating a degree of 3, it is exactly matching the actual points. And that is the reason why we are getting so strong R2 value. Can we change the value to degree 4? The answer is yes. Let's see what happens if we change the value to degree 4. We still get a 91 point. So it has reduced slightly. Why? Because it also has to accommodate for the degree 4, right? Now in doing so, 100% it gives more weightage to x cube. However, x to the power 4 also plays a slight role. So the model becomes confused and it also gives some weightage to x4. The reason why the R2 value decreases a bit. You can take, let's say, if I take degree equals to 14, we'll see probably a slight decrease, a lot of decrease, right? Actually. So choosing the degree is also an art, right? Based on the model, based on your SMEs, you have to figure out which one would be the best degree that you need to choose. Okay, not always does our graph looks so easy to interpret, right? All right. So this was all about polynomial regression, and I hope you understood how we changed or how we tweaked the same linear regression model to fit a non-linear distribution. And how did we increase the R2 score? By using this polynomial regression, right? Great. See you in the next video. Thank you.